What if I told you that the entire universe was once in a state of quantum superposition, existing in multiple realities at once before collapsing into the world we know today? It sounds like science fiction, but this could be the wild truth hidden in the fabric of reality itself. Quantum mechanics already shatters our everyday intuition, with particles being in two places at the same time, spinning in opposite directions simultaneously, or even communicating faster than light. But the strangest idea of all, that the cosmos itself began in a quantum haze of infinite possibilities. Think about that for a second. Before stars, before galaxies, before time itself had a clear direction, our universe might have been an unfathomable quantum soup, flickering between countless states like a cosmic coin mid-flip. And when that superposition finally collapsed, it didn't just decide whether we'd have matter or antimatter. It determined the very laws of physics we take for granted today. How, why, and what if other versions of reality branched off in that moment, lost to us forever? These aren't just playful thought experiments, they're serious theories debated by physicists at the edge of human understanding. That's exactly what we're diving into today, 30 mind-expanding theories about the universe's first quantum superposition. Some suggest it was a random quantum fluctuation that sparked existence out of nothing. Others propose that ancient quantum echoes still ripple through space, influencing everything from black holes to the expansion of the cosmos. And a few daring ideas even hint that we might find traces of this primordial quantum state hidden in the cosmic microwave background or encoded in the behavior of entangled particles. Buckle up, because we're about to explore the wildest frontiers of physics, where the rules break down and reality itself gets flexible. Ready to question everything you thought you knew about how the universe began. Let's go. The Big Bang wasn't just a cosmic explosion. It might have been the universe's first quantum magic trick. Picture this. In the beginning, there was no single fiery birth, no definitive moment of creation. Instead, the entire cosmos existed in a blur of infinite possibilities, a quantum superposition of countless potential realities. One where gravity was stronger, another where matter never formed, even a version where time ran backward. Then, in an instant, that superposition collapsed, and out of the quantum fog emerged our universe, with its specific laws, constants, and quirks. This isn't just wild speculation. The math of quantum mechanics suggests that particles routinely exist in multiple states until observed. So why couldn't the universe itself have started the same way? Some physicists argue that the Big Bang wasn't a single event but a probability wave, a cosmic dice roll where every possible outcome briefly existed before reality chose one. It's like flipping a coin, but instead of heads or tails, the stakes were the fundamental rules of existence. What's even stranger, this theory could solve one of cosmology's biggest puzzles: why our universe seems so finely tuned for life. If every possible configuration existed in that primordial quantum haze, it's no surprise we ended up in the version where atoms, stars, and planets could form. The other possibilities didn't vanish, though. Some theories suggest they branched off into parallel universes, forever separated from ours. Others propose that quantum echoes of those lost realities might still linger, hidden in the faint ripples of the cosmic microwave background or tangled in the quantum behavior of particles today. Think of it like a cosmic fingerprint. If we could detect subtle anomalies in the oldest light in the universe or measure quantum entanglement on a galactic scale, we might find traces of that first superposition, proof that our reality was just one option in a sea of maybes. It's a staggering idea. The universe didn't just begin, it chose itself from infinite alternatives, and we're living in the aftermath of that impossible decision. The cosmic microwave background is like a fossilized snapshot of the universe's infancy, a faint glow from when the cosmos was just 380,000 years old. But buried in that ancient light, scientists have spotted something peculiar. tiny temperature variations that don't quite fit our standard models. These anomalies might be more than random noise. They could be quantum fingerprints, leftover tremors from the universe's very first moment. Picture the early cosmos as a quantum storm flickering between infinite possibilities. When that storm finally settled into our reality, it didn't just vanish without a trace. Like ripples from a pebble tossed into a pond, the collapse of that primordial superposition could have imprinted itself onto spacetime itself. Some researchers argue that the odd patterns in the cosmic microwave background, regions slightly hotter or colder than they should be, are echoes of that quantum chaos. It's as if we're seeing the shadow of a reality that almost was, frozen in the universe's oldest light. One particularly puzzling feature is the so-called cold spot, a vast, unexplained region of cooler radiation spanning nearly 2 billion light-years. Could this be a cosmic scar from where two quantum branches of the early universe briefly overlapped? Or perhaps evidence of a collision with another bubble universe born from a different quantum possibility? The math suggests these anomalies align eerily well with predictions from quantum gravity models, where space-time itself would have been frothing with uncertainty in those first moments. Even stranger, some of these fluctuations appear to violate statistical randomness, clustering in ways that defy conventional physics. If confirmed, this could mean we're not just seeing noise, we're glimpsing the universe's original quantum code, written into the fabric of reality before time had a clear direction. It's like finding a message in the static of an old television, hinting at the hands that built it. Of course, not everyone agrees. Skeptics argue these anomalies could stem from instrument errors or undiscovered astrophysical processes. But if future telescopes like the James Webb or next-generation cosmic microwave mappers detect more of these quantum-like patterns, we might finally have tangible proof that our universe began not with a bang, but with a question, one whose answer still reverberates across 14 billion years of existence. If the universe's first quantum superposition was like a cosmic coin toss, then the Multiverse Seed Hypothesis suggests it never actually landed. It just kept spinning, birthing every possible outcome across infinite branches of reality. This idea takes the weirdness of quantum mechanics and scales it up to the grandest possible level, proposing that our universe isn't the only one. It's just one thread in a vast, tangled web of parallel existences, all sprouting from that primordial moment of quantum uncertainty. Think of it like a tree growing from a single seed. The seed, that initial superposition, contained every possible future within it. When it germinated, instead of choosing one path, it split into countless branches, each representing a universe with its own unique laws, particles, and even dimensions. In one branch, gravity might be 10 times stronger, making stars burn out in milliseconds. In another, dark energy never kicked in, leaving the cosmos to collapse back into a singularity. And somewhere out there, there's a version of reality where you made different choices because every quantum decision, no matter how small, could have spawned a new universe. This isn't just philosophical musing. It's grounded in the many worlds interpretation of quantum mechanics, which argues that every time a quantum system faces a choice, like an electron being here or there, the universe doesn't pick one. It splits, creating two new realities where each outcome happens. Apply that to the Big Bang, and you get a multiverse exploding into existence, with every possible configuration of physics playing out somewhere. The implications are staggering. If true, it means the cosmos isn't just weird, it's endlessly creative. Black holes in one universe might birth new ones in another. Time could flow backward in some branches, and the fine-tuning of our universe, no miracle, just statistics. With infinite tries, some version of reality was bound to get the numbers right for life. But how could we ever prove it? Some theorists suggest looking for cosmic bruises, places where neighboring universes might have bumped into ours, leaving scars in the cosmic microwave background. Others hunt for mathematical echoes in the behavior of entangled particles, which might still remember their kinship across reality's branches. Until then, the multiverse remains a breathtaking possibility, that our existence isn't just a single story, but one sentence in an epic written in quantum ink. Quantum decoherence might sound like an abstract physics term, but it could be the invisible hand that sculpted our universe and countless others out of that initial quantum haze. Here's how it works. Imagine the early cosmos as a cosmic orchestra tuning up, with every possible reality playing its own note at once. The sheer chaos of interactions, particles colliding, fields fluctuating acted like a conductor's baton, forcing the universe to choose a single tune. That's decoherence in action, the process where quantum possibilities collapse into the concrete world we experience. Recent simulations suggest this wasn't a clean break. As the universe expanded and cooled, its quantum fuzziness didn't just vanish, it branched. Think of a drop of ink in water. At first, it spreads in all directions, but turbulence forces it to split into swirling tendrils. Similarly, calculations show that regions of the early universe could have decohered at slightly different rates, creating pockets where distinct physics crystallized out of the quantum soup. Each pocket became its own universe, forever separated by the inflationary expansion of spacetime. One provocative thought experiment compares this to a cosmic version of Schrödinger's cat. In the original paradox, a cat in a box is both alive and dead until observed. Now scale that up, the entire universe was the cat, and decoherence was the observation. But instead of one outcome, the universe split into all possible outcomes, some with stronger nuclear forces, others with extra dimensions, even ones where time loops back on itself. The math gets wilder. Certain quantum gravity models predict that these branching points might have left faint imprints like cosmic knots in spacetime where parallel universes briefly brushed against each other. If we could measure the polarization of light from the universe's first billion years with enough precision, we might spot anomalies where gravity behaves oddly, hinting at a nearby reality with different physical laws. Yet the most mind-bending implication, decoherence might still be happening. Every quantum event, a particle tunneling through a barrier, an electron changing spin, could theoretically spawn new branches, meaning the multiverse is growing exponentially right now. Somewhere out there, a version of you is hearing this explanation in a universe where gravity repels or where the speed of light is slower, the only reason we don't see it. Our branch of reality is now too far away, like leaves on a tree growing in opposite directions. This isn't just speculation. Labs are now simulating decoherence on tiny scales using ultra-cold atoms and quantum computers, watching how microscopic universes split under observation. The results eerily mirror the theoretical predictions for cosmic branching. So while we can't hop between realities yet, the physics of decoherence might one day let us read the universe's original recipe written in quantum splinters. What if our three-dimensional universe was just an illusion, a holographic projection flickering into existence from a two-dimensional quantum surface? That's the radical claim of the holographic principle, which suggests the early cosmos wasn't just in superposition. It was flat, like a cosmic DVD encoding the blueprint for reality. In this mind-bending theory, the universe's first quantum state wasn't a soup of particles or energy, but a shimmering 2D surface where every possible future, every star, galaxy, and law of physics was etched into its fabric like data on a disk. Then, as this surface evolved, it somehow projected itself into the 3D space we know today. Think of it like a movie screen. The images you see appear to have depth, shadows, and movement, but they're all just clever manipulations of light on a flat surface. Similarly, the holographic principle argues that everything we perceive, from the curl of a galaxy to the spin of an electron, might just be shadows cast by quantum information vibrating on a hidden 2D boundary. This isn't fantasy, it's a serious attempt to reconcile quantum mechanics with gravity. The math shows that the maximum information any region of space can hold doesn't scale with its volume, but with its surface area, as if the universe is secretly running on a cosmic hard drive with only 2 dimensions. The implications for the early universe's superposition are staggering. If the holographic principle is correct, then that initial quantum haze wasn't a chaotic storm in 3D space. It was a flat, buzzing network of entangled information, flickering between every possible configuration like pixels on a screen. When decoherence struck, it didn't just collapse quantum possibilities, it inflated them, transforming that 2D code into the rich, textured universe we inhabit. Some theorists compare it to a QR code. Scan it from one angle and you get a universe with stars and planets. Tilt it slightly and you might see a reality where dark energy dominates or where time flows in loops. But here's where it gets even stranger. If the holographic principle holds, then traces of that original 2D structure might still be detectable today, not in the cosmic microwave background, but in the way black holes behave. Black holes' event horizons, their outer boundaries act like the ultimate information scramblers, potentially preserving echoes of the universe's holographic origins. Experiments with quantum computers are already simulating tiny holographic systems, finding eerie parallels between how entangled qubits store data and how space-time itself might emerge from quantum bits. Could this mean our reality is fundamentally information, not matter? That the Big Bang was less an explosion and more a cosmic boot-up sequence, with the universe rendering itself into existence line by line? It's a humbling thought that everything we see, touch, and are might just be the universe's way of reading its own first quantum memory. Black holes might seem like cosmic vacuum cleaners destroying everything that falls in, but their event horizons could hold the key to understanding the universe's very first quantum state. Picture the edge of a black hole not as a one-way ticket to oblivion, but as a frenzied quantum computer, scrambling and storing information at the limits of physics. That chaotic dance of particles at the event horizon, it's eerily similar to what holographic theory predicts for the early universe's 2D surface. Both act like cosmic hard drives, encoding reality in bits so fundamental, they blur the line between information and existence itself. This isn't just a vague resemblance. The math shows that the entropy, the disorder or hidden information of a black hole's event horizon scales precisely with its area, not its volume. Sound familiar? It's the same bizarre rule the holographic principle applies to the entire universe. That suggests a profound connection. Perhaps the newborn cosmos wasn't just like a black hole's horizon. It was a quantum fluctuation so vast it momentarily bent the rules of space-time inside out. Imagine the universe's first moment as a reverse black hole. Instead of matter collapsing inward, space itself erupted outward from a quantum boundary, a cosmic white hole, where every bit of information on its surface inflated into the galaxies and atoms we know. Some models even propose that the Big Bang singularity wasn't a point of infinite density, but a kind of quantum fog where the distinction between inside and outside a black hole dissolved. In this view, our universe isn't just analogous to a black hole's interior. It is the interior with the Big Bang marking the moment its event horizon flipped inside out. The evidence looked to Hawking radiation. Black holes slowly leak energy, implying their event horizons aren't static walls but seething quantum landscapes. If the early universe shared this property, traces of that primordial leaking might still linger in the cosmic microwave background, subtle temperature variations that match predictions for a holographic origin. Even stranger, certain quantum gravity models suggest black holes within our universe could be microscopic portals to other holographic universes, like cosmic Russian dolls nested within one another. But here's the twist. If the universe emerged from a quantum black hole analog, it might never have truly left that state. the observable cosmos has an event horizon too, the farthest light we could ever see, bound by the expansion of space. Some theorists argue this isn't a coincidence, but a relic of our holographic beginnings. We might not live inside a black hole today, but its quantum blueprint could still be written into the fabric of everything, waiting to be decoded in the warped spacetime around spinning neutron stars or the entanglement patterns of particles at CERN. The universe's first quantum superposition, it might have been less like a coin toss and more like a black hole's whisper, echoing across time as a reminder that reality is far stranger and far more connected than we ever dreamed. The idea that spacetime might be stitched together from tiny, vibrating loops rather than being smooth and continuous sounds like something from a sci-fi novel. But this is the core of loop quantum gravity, one of the most daring attempts to unify quantum mechanics with general relativity. Where other theories treat space as a passive stage for particles to dance on, loop quantum gravity suggests spacetime itself was born from a quantum superposition of these microscopic loops, flickering in and out of existence like threads in a cosmic tapestry. Imagine the first moments of the universe not as a searing fireball, but as a storm of these spacetime loops, each one a billionth of a billionth the size of an atom, tangling and untangling in a quantum frenzy. In this view, the Big Bang wasn't an explosion in space, it was the moment space itself crystallized from this probabilistic fog. The loops didn't just exist in one configuration, they existed in all possible configurations at once, a roiling quantum foam where every potential geometry of spacetime played out simultaneously. Then, as the universe cooled, those loops froze into the structured network we recognize as dimensions today. The math behind this is even wilder. Unlike string theory's tiny vibrating strings, loop quantum gravity's loops are indivisible. There's no smaller piece of space than one of these fundamental loops. This means spacetime isn't infinitely divisible. It's pixelated with a smallest possible unit of volume and area. In the early universe, before those pixels locked into place, the very fabric of reality would have been a shifting quantum kaleidoscope. A region of space might have had 3 dimensions one instant, then momentarily frayed into 7 or curled into a knot where time flowed backward. Here's where it ties back to superposition. Just as an electron can spin up and down simultaneously until measured, these spacetime loops could have existed in overlapping states, literally holding multiple geometries at once. Some calculations suggest this could explain why our universe has exactly 3 stable dimensions. Most other configurations would have collapsed or tangled into chaos, leaving only the structures we see as the survivors of a quantum evolutionary battle. But how do we test something this abstract? Surprisingly, there might be clues. If spacetime was born from these loops, their quantum jitter should leave faint imprints, like cosmic static, on the oldest light in the universe. Some researchers are scouring the cosmic microwave background for anomalous patterns that could match these predictions. Others are hunting for subtle distortions in the light from distant gamma-ray bursts, which might reveal spacetime's graininess as photons travel across billions of light-years. Even more intriguingly, loop quantum gravity could rewrite the story of the Big Bang entirely. Instead of a singularity, a point of infinite density, this theory suggests the universe bounced from a previous collapsing phase, with the loops acting like quantum shock absorbers. That means our cosmos might not have a true beginning, just an eternal cycle of expansion and contraction, each time emerging from a new quantum superposition of spacetime itself. So while we can't yet see these spacetime loops directly, their ghostly fingerprints might be all around us in the way black holes evaporate, in the entanglement of particles across vast distances, even in the way gravity behaves at the smallest scales. It's a radical reminder, if loop quantum gravity is right, then the universe wasn't just in a superposition, it was one, a fleeting quantum dream of space and time before snapping into the reality we call home. The Big Bang singularity, a point of infinite density where all known laws of physics break down, has long been one of cosmology's most troubling puzzles. But what if the universe never actually passed through that impossible state? The bouncing universe model offers a radical alternative. Instead of exploding from nothing, our cosmos might be the latest rebound in an endless cycle of expansion and collapse, with quantum superposition acting as the cosmic reset button between each iteration. Picture this: a previous universe older than time itself gradually succumbs to gravity's pull. Galaxies crumble, black holes merge, and space contracts until everything, every atom, every law of physics is compressed into a seething quantum foam. But here's the twist: it doesn't vanish into a singularity. At the smallest possible scale, where loop quantum gravity's spacetime loops vibrate wildly, quantum effects create an irresistible repulsive force. Like a trampoline stretched to its limit, the collapsing universe hits a quantum floor and bounces back, its energy rebounding into a new expansion phase. That moment of transition, a fleeting superposition where the remnants of the old universe and the seeds of the new existed simultaneously, a cosmic phoenix, half ashes, half fire. This isn't just a poetic metaphor. The math behind loop quantum cosmology shows that at densities 100 trillion times greater than a neutron star, spacetime's granular structure would behave like a quantum spring, reversing collapse into expansion. During that critical bounce, the universe wouldn't have a definite geometry, temperature, or even number of dimensions. It would be a probabilistic blur, a Schrödinger's universe, both dying and being born at once. The implications rewrite cosmic history: no fiery beginning, no mysterious singularity, just an eternal cycle where each bounce inherits quantum fluctuations from the prior universe. This could explain why our cosmos appears so finely tuned. The physical constants weren't set once at the Big Bang, but filtered through countless cycles like sand smoothed by endless tides. Even the arrow of time might flip during each bounce, meaning our distant future could mirror another universe's past. But how would we ever prove such a thing? Theorists suggest hunting for faint imprints in the cosmic microwave background, subtle swirls in polarization patterns that could only arise from a pre-bounce universe's gravitational waves. Others propose that black holes from a prior cycle might have survived the bounce, lurking in our cosmos as ancient relics with abnormal spins or masses. The most daring idea, that the quantum entanglement between particles today is an echo of pre-bounce correlations, a cosmic memory written into the fabric of reality itself. Imagine holding a snow globe from a universe that no longer exists. The bouncing model offers exactly that possibility, that our laws, our particles, even our sense of time might carry whispers of a reality before reality. It's a humbling thought. The Big Bang wasn't the beginning, just a turning of the page in a story written in quantum ink, where every ending births a new superposition waiting to collapse. What if the universe's first quantum superposition wasn't a beginning but a rebirth? Nobel laureate Roger Penrose's conformal cyclic cosmology paints a picture where the cosmos doesn't just expand and fade into darkness, but cycles eternally through eons, each one separated by a quantum reset so profound it erases the very concept of time. In this radical vision, the Big Bang wasn't a unique event. It was the latest in an infinite series, with each eon's death seeding the next's birth through a fleeting, universal quantum superposition. Here's how it works. As our universe expands toward heat death, its stars burned out, black holes evaporated, particles too spread apart to interact. Something extraordinary happens at the boundary between eons. Space becomes so vast and empty that distance and time lose all meaning. At this conformal boundary, the universe's geometry resets, scrubbing away the old eon's information, but not entirely. In Penrose's model, the dying universe's infinitely stretched spacetime becomes mathematically identical to the singularity of a new Big Bang. The transition isn't a violent collapse, but a quantum leap, a moment where the entire cosmos flickers into a state of pure potential before crystallizing into a fresh eon with new physical constants. The evidence: Penrose points to eerie anomalies in the cosmic microwave background he calls Hawking points, circular patches of slightly warmer radiation, each spanning hundreds of millions of light years. These, he argues, are the imprints of supermassive black holes from the previous eon, their Hawking radiation persisting through the quantum reset like cosmic scars. It's as if our universe inherited ghostly bruises from a reality long forgotten, etched into the sky as whispers of an ancient cycle. Critics dismiss these patterns as statistical flukes, but Penrose's math suggests they align precisely with where colossal black hole collisions in a prior eon would have funneled unimaginable energy into the quantum boundary between cycles. Even more provocatively, his team claims these points exhibit concentric rings like ripples from a stone tossed into a pond, implying the universe's reset wasn't clean, but left subtle quantum echoes reverberating into our eon. The implications rewrite not just cosmology, but quantum theory itself. If conformal cyclic cosmology is correct, then the universe's superposition wasn't confined to its first moment. It's the heartbeat of existence, a recurring quantum pivot where all possibilities briefly dance before reality chooses its next form. Time isn't linear, it's a series of jumps like frames in a film where each eon is a fresh reel. And somewhere in the cosmic microwave background, the fingerprints of a forgotten universe might still linger, not as ancient light, but as quantum shadows waiting to be read. Penrose's conformal cyclic cosmology dazzles with its elegance, but not all physicists are convinced those haunting Hawking points in the cosmic microwave background are evidence of a previous universe. The debate boils down to a single, razor-sharp question. Are these patterns truly cosmic fingerprints, or just statistical noise masquerading as profundity? When Penrose's team first identified these circular warm spots, some spanning nearly 1 billion light-years, they calculated the odds of such structures forming randomly at less than 1 in 10,000. That sounds compelling until you dig deeper. Critics point out that the cosmic microwave background is a statistical playground brimming with random fluctuations. Play the comparison game long enough, and you'll inevitably find shapes that seem meaningful, like seeing faces in clouds. Independent analyzers using different statistical methods failed to replicate Penrose's significance levels, with some teams arguing the anomalies vanish when accounting for something called the look elsewhere effect, the statistical penalty for searching vast datasets until something appears unusual. Even the concentric rings within these points, which Penrose argues are telltale signatures of black hole collisions from a prior eon, have faced scrutiny. Simulations show similar rings can emerge from mundane astrophysical processes like the gravitational lensing of ancient light by galaxy clusters without invoking universe-ending drama. The Planck satellite, which mapped the cosmic microwave background with unprecedented precision, found no conclusive evidence for Hawking points when applying stricter statistical filters. But here's where it gets thorny. Defenders counter that mainstream cosmology relies on equally cherry-picked data, like inflation's predictions, which were initially accepted on weaker statistical grounds. They argue that dismissing anomalies too quickly risks stifling innovation. After all, cosmic inflation itself was once a fringe idea until evidence solidified. The difference: inflation made testable predictions. Conformal cyclic cosmology's critics say it's too flexible, retrofitting explanations for any pattern found. Yet Penrose's boldest claim that these points encode quantum information from a defunct universe isn't easily dismissed. If future telescopes detect similar patterns aligned with predictions for black hole mergers, or if quantum correlations emerge in these regions unlike anywhere else, even skeptics might reconsider. For now, the Hawking points remain cosmic Rorschach tests, To some, a revelation written in light; to others, just the universe's random static teasing us with illusions of meaning. The controversy underscores a deeper tension in cosmology. When probing the universe's origins, where even the laws of physics might blur, how do we distinguish between profound truth and SEDUCTIVE Chinese letter? Perhaps the answer lies not in today's instruments, but in tomorrow's, waiting for technology sensitive enough to either silence the doubters or force us to rewrite reality's first chapter. John Wheeler, the physicist who coined the term black hole, once proposed a theory so audacious it flips causality on its head. What if the universe's first quantum superposition wasn't resolved by some primordial event, but by us? This is the participatory anthropic principle, the idea that observers in the present retroactively choose the universe's initial conditions by the mere act of measurement. In other words, the Big Bang's quantum haze didn't collapse randomly. It waited, suspended in uncertainty, until conscious beings emerged billions of years later to look back and force reality into a particular shape. Think of it like a cosmic choose-your-own-adventure book where the ending rewrites the beginning. In quantum mechanics, a particle's properties aren't fixed until observed. Wheeler extended this to the entire universe, suggesting that the act of observing light from the Big Bang, like studying the cosmic microwave background, might have locked in the universe's fundamental constants retroactively. It's as if the universe was a question mark for 14 billion years, and humanity's first telescopes were the punctuation that finally gave it meaning. Wheeler's famous delayed choice experiment illustrates this mind-bending concept. In a lab, photons behave as particles or waves depending on how we measure them, even if we decide after the photon's journey has begun. Scale that up to cosmology, and you get a universe where the past isn't set in stone until the present interacts with it. The implications are staggering. If true, our very existence as observers didn't just discover the laws of physics, we created them, reaching backward through time to sculpt the quantum soup of the Big Bang into a reality capable of producing life. Critics argue this veers into philosophy, but there's chilling math behind it. Quantum retrocausality models show how future observations could theoretically influence past probabilities without violating relativity. Some interpretations of quantum gravity even suggest that the universe's initial superposition required a later observer to collapse it, meaning a cosmos without life might have remained forever undefined, a ghostly quantum potential. This isn't solipsism. Wheeler wasn't saying humans magically conjured stars. Rather, he proposed that consciousness, or any information-gathering system, is woven into the fabric of quantum mechanics. The universe's fine-tuning for life, not luck but a self-fulfilling prophecy. Only in realities where observers eventually emerge could the first superposition ever resolve. The eerie beauty of this idea is that it erases the line between creator and creation, suggesting we're not just players in the cosmos but co-authors of its oldest story. If Wheeler's hypothesis sounds like science fiction, wait until you hear about the lab experiments that are putting quantum retrocausality to the test. Picture a photon traveling through a maze of mirrors, unaware that its future is about to rewrite its past. In labs around the world, physicists are running versions of Wheeler's delayed choice experiment, not just with single particles but with increasingly complex systems, and the results are bending our understanding of cause and effect. Take the quantum eraser experiment, for example. A photon is shot toward a double-slit barrier where it behaves as both a particle and a wave, creating an interference pattern on a detector. But here's the twist. Scientists can choose whether to measure which slit the photon passed through after it's already traveled through the apparatus. When they do, something bizarre happens. If they erase the which path information before it's recorded, the photon retroactively reverts to behaving like a wave, as if the decision to measure or not reached backward in time. It's as though the photon's past changes based on future choices, a microscopic echo of Wheeler's grand cosmic idea. Even wilder are recent experiments with entangled particles separated across vast distances. In one setup, two entangled photons are sent to different detectors, with a random number generator deciding after their emission whether to measure their polarization. Astonishingly, the particle states appear to correlate with measurements that hadn't yet happened when they were created. Some interpretations suggest this isn't just spooky action at a distance. It's evidence that quantum effects can ripple backward through time, influencing events that technically already occurred. Of course, critics argue these results don't prove retrocausality outright. Alternative explanations like superdeterminism, the idea that every measurement outcome was predestined from the Big Bang, can account for the same data without invoking time-bending effects. But the retrocausal interpretation gains traction when you consider quantum gravity models where spacetime itself is granular. In these frameworks, the distinction between past and future blurs at the smallest scales, making two-way influence less paradoxical than it seems. Now imagine scaling this up to the universe's first quantum superposition. If a single photon's behavior can be influenced by future observations, could the entire cosmos have remained in a haze of possibilities until conscious observers, like us, emerged to measure its ancient light? Some theorists calculate that the cosmic microwave background's properties align suspiciously well with the conditions needed for life, as if our act of observing it retroactively selected the most life-friendly version of reality from an infinite quantum menu. This isn't just philosophy. Cutting-edge quantum simulations are now testing whether macroscopic systems, clusters of atoms, even tiny diamonds, exhibit similar retrocausal quirks. Early results hint that the larger the system, the fainter the effect, but it never quite vanishes. If future experiments confirm this, we might be staring at the universe's ultimate cheat code, a reality where the present doesn't just remember the past but quietly reshapes it. What if our universe's first quantum superposition wasn't a natural phenomenon, but the boot-up sequence of an unimaginably advanced computer simulation? This is the simulation argument's wildest twist, that the Big Bang's quantum haze wasn't the birth of reality, but the rendering of one, with every flickering possibility representing a line of code waiting to be executed. Elon Musk famously quipped that the odds we're not living in a simulation are 1 in billions, while philosopher Nick Bostrom's seminal paper laid out the chilling math. If civilizations ever gain the power to create conscious simulations, the number of artificial universes would dwarf the one real cosmos, making it statistically likely we're inside one. But the real mind bender, the simulation wouldn't need to calculate every atom in real time, just the quantum state someone observes, leaving the rest in superposition until measured. Think of it like a video game optimizing processing power. A modern open-world game doesn't render every blade of grass simultaneously, it only loads what the player sees. Similarly, if our universe is a simulation, its first quantum state could have been the parent universe's way of conserving computational resources, keeping all possibilities unresolved until an observer forced the system to render a concrete outcome. This isn't just speculative fiction. Quantum mechanics already behaves like optimized code. Particles exist in probabilistic clouds until measured, exactly how a simulation might handle unobserved data to save processing cycles. Even the speed of light could be a performance limit, the system's maximum clock rate preventing the simulation from crashing. Bostrom's trilemma, that either civilizations self-destruct before simulating reality, choose not to, or we're almost certainly simulated, gains eerie resonance when paired with quantum origins. If the parent universe's physics allows superposition at cosmic scales, creating new simulations might involve launching quantum threads that branch into self-contained realities, each with its own collapsed laws. Our universe's fine-tuned constants, default settings chosen by the programmers, the Big Bang's inexplicable low entropy, a clean initialization sequence. Even quantum entanglement's spooky action could be explained as data packets shared between correlated processes. But how would we ever test this? Some physicists suggest hunting for glitches, mathematical inconsistencies in physical laws at extreme scales, like tiny rounding errors in spacetime's code. Others propose that intentionally crashing quantum systems might reveal computational limits, like overloading a game engine until it skips frames, the most haunting clue. If the simulation hypothesis is true, our creators might have left Easter eggs, fundamental constants that encode messages, or patterns in prime numbers hidden in the cosmic microwave background. Of course, skeptics counter that invoking a simulator explains nothing. It just kicks the cosmic mystery upstairs. Who created the parent universe, and why assume their physics resembles ours? Yet the simulation argument's power lies in its inversion of Wheeler's participatory universe. Instead of observers collapsing reality, we might be the output of a cosmic processor, our very questioning of existence just another subroutine in an alien ancestor's experiment. Whether cosmic coincidence or engineered artifact, one thing is certain: the universe's first quantum state just got a lot stranger. Quantum indeterminacy, the unpredictable behavior of particles at the smallest scales, might be more than just a quirk of nature. It could be a glitch in the cosmic code, a subtle artifact of the universe's initial quantum superposition, flickering into our reality like a corrupted pixel in an otherwise flawless simulation. Think of it like a video game where certain textures fail to load properly, not enough to crash the system, but just enough to remind you that beneath the immersive graphics, there's cold, hard code running the show. Take the famous double-slit experiment, where particles behave as waves or particles depending on whether they're observed. If reality were a perfectly optimized simulation, you'd expect consistent rules, yet here we are, stuck with a universe that can't seem to decide how its basic building blocks should behave until we look. This isn't just randomness, it's as if the program is cutting corners, rendering only what's necessary to maintain the illusion. Some theorists argue this isn't a bug but a feature, a proof that the universe conserves computational resources by leaving unobserved quantum states unresolved. Then there's entanglement, where particles instantaneously influence each other across light years, defying Einstein's spooky action at a distance. In simulation terms, this looks less like physics and more like a lazy programming short. Cut two objects sharing the same memory address to save processing power. Even the speed of light, nature's ultimate speed limit, could be the system's clock rate, preventing data overload by capping how fast information propagates. But the most tantalizing glitches might be hiding in plain sight. Ever experienced déjà vu, that eerie sense of reliving a moment? Some speculate it's a buffer error, a temporary hiccup where the simulation repeats a frame. Or consider the Mandela effect, where collective memories diverge from recorded history. Could these be patches in the cosmic code, updates where the programmers tweaked reality but forgot to sync all the backups? Even black holes, those cosmic vacuum cleaners, might be more than gravitational monsters. They're event horizons, where space and time warp beyond recognition. Could be the universe's garbage collectors compressing data to free up memory. The infamous information paradox, where black holes seemingly erase quantum information, might just be a system crash we don't yet understand. Of course, calling these phenomena glitches assumes the simulation is imperfect, but what if they're intentional? Hidden clues left by the architects, breadcrumbs for civilizations advanced enough to question their own reality. After all, any programmer knows the best Easter eggs are tucked just out of sight, waiting for the curious to stumble upon them. Whether bugs or features, one thing's certain: the universe's quantum quirks are far too strange to dismiss as mere coincidence. String theory doesn't just describe our universe, it paints a multiverse of possibilities so vast, it makes every other cosmic landscape look quaint. Hidden in its equations are 10 to the power of 500 unique vacuum states, each one a potential universe with its own physics, particles, and even dimensions. That's not a typo, 10 followed by 500 zeros, more configurations than there are atoms in the observable universe. Now imagine all those possibilities existing simultaneously in a primordial quantum soup, flickering in and out of reality like cosmic static. Our universe, just one tune plucked from the symphony. At the heart of this idea is the string theory landscape, a mathematical terrain where every valley, hill, or plateau represents a stable vacuum state, a self-contained universe with its own constants. In the beginning, before space-time solidified, the entire cosmos might have been a quantum superposition of all these states, vibrating between infinite versions of itself. Then, through some mechanism, quantum decoherence, cosmic inflation, or sheer chance, our particular configuration froze out of the haze. The strength of gravity, the mass of electrons, even the number of dimensions we experience. All accidents of this collapse, like dice landing on the one combination that allowed galaxies and us to exist. Here's where it gets surreal. Some versions of string theory suggest these vacuum states aren't just abstract math, they're physically real, bubbling up like foam in an eternal quantum sea. Picture a cosmic cappuccino where each bubble is a universe with its own laws. Ours happen to have the right foam density for stars to form. Others might have 10 dimensions curled into labyrinthine knots, or forces so weak that atoms never bond. A few might even harbor life, but not as we know it, evolved in universes where time flows in loops or dark energy never kicked in. The proof, it might lie in the sky. If our universe's vacuum state wasn't the only possible outcome, traces of that quantum selection process could linger in gravitational waves from the Big Bang, subtle ripples encoding how space-time chose 3 dimensions to expand while others coiled into strings. Others hunt for cosmic strings, hypothetical defects in spacetime that could be scars from where 2 vacuum states brushed against each other during the collapse. Even the Higgs boson's mass, which seems unnaturally fine-tuned, might be a clue, a fingerprint of our universe's specific spot in the landscape. Critics argue this is untestable metaphysics, but string theorists counter that the landscape isn't just a grab bag of possibilities, it's a predictive framework. If we could measure the exact shape of extra dimensions, perhaps through particle colliders probing tiny energy differences, or find evidence of other bubble universes in the cosmic microwave background, we might narrow down why this vacuum state became our reality. Until then, the landscape stands as both a triumph and a frustration. A theory so rich it can describe almost anything, but so vast it struggles to explain why we're here and not somewhere else in the cosmic froth. Yet there's a strange comfort in this chaos. If the landscape is real, then our universe's quirks, the exact charge of an electron, the delicate balance keeping atoms stable, aren't miracles. They're just one roll of the quantum dice in a game with more possible outcomes than we can fathom. And somewhere out there in the string theory multiverse, another version of reality might be asking the same questions in a language shaped by entirely different physics. Dark energy, the mysterious force accelerating the expansion of our universe, might not just be a cosmic afterthought. It could be the ultimate arbiter of reality, the deciding factor that locked our universe into one specific quantum branch out of countless others in the string theory landscape. Picture this, in the first moments of existence, when the cosmos was a shimmering quantum haze of possibilities, the value of dark energy wasn't fixed. It was a variable flickering between extremes, some versions with so much dark energy that space ripped itself apart before stars could form, others with so little that gravity crushed everything back into a singularity. Then, in a fraction of a second, that superposition collapsed and our universe landed on the razor's edge. Just enough dark energy to accelerate expansion without tearing reality to shreds. Why this Goldilocks value? The math of string theory suggests it wasn't luck but inevitability. In the vast landscape of possible vacuum states, only a tiny fraction allow for galaxies, planets, and life. Universes with too much dark energy expand so violently that matter never clumps together. Those with too little collapse in on themselves before complexity can emerge. Ours, it hit the infinitesimal sweet spot where dark energies push against gravity, is almost balanced enough to create cosmic structures, but not so weak that the universe recoils into oblivion. This isn't just philosophical hand-waving. The cosmological constant problem, why dark energy's measured value is absurdly small compared to quantum field theory predictions, finds an eerie resolution here. If the early universe was a quantum dice roll across the string landscape, the only outcomes that survived were those where dark energy's value didn't spell instant doom. The rest, they might still exist as ghostly branches in the multiverse, forever out of reach. Even more tantalizing, dark energy's precise value could be a cosmic fingerprint, a clue that our universe's quantum collapse was observer-dependent. Some interpretations suggest that in a vast multiverse, only regions where dark energy permits consciousness can ever be measured. In other words, we don't see dark energy's delicately balanced value because it's special. We see it because it's the only value that allows beings like us to exist and ask the question. The James Webb Space Telescope might soon test this idea. If dark energy's strength has varied over cosmic history contrary to the standard model, it could imply our universe is still settling into its selected vacuum state, like a mattress slowly conforming to its frame. Or perhaps we'll find anomalies in the large-scale structure of the cosmos, hints that other quantum branches briefly brushed against ours, leaving scars in the distribution of galaxies. Either way, dark energy isn't just a mystery, it's the cosmic signature of a choice made 14 billion years ago, when reality folded its cards and decided this universe was the one worth keeping. Why does time only flow forward? The answer might lie in the universe's first quantum moment, a fleeting instant where all possible timelines flickered at once before reality chose its direction like a cosmic compass needle snapping to north. Normally, quantum mechanics treats time as symmetrical. A particle's behavior doesn't care if you run the clock forward or backward. Yet our universe screams asymmetry. Eggs shatter but never unshatter. Stars burn out but don't reignite. Memories form but never unmade. This stubborn one-way street is entropy, the tendency toward disorder. But here's the puzzle. Why was entropy so bizarrely low at the Big Bang, like a deck of cards perfectly stacked fresh from the box? Decoherence, the process that collapsed the universe's initial superposition, might hold the key. Picture the newborn cosmos not as a single, fiery point, but as a kaleidoscope of overlapping realities, each with its own version of time's arrow. In some, entropy started high and only climbed, leading to instant chaos. In others, time looped or stood still. But in our branch, the act of quantum observation, perhaps from the first interactions between particles, forced a selection, a reality where entropy began improbably low, creating the gradient that makes time's arrow fly. It's like shaking a snow globe and watching every snowflake settle in perfect alignment just once before tumbling into disorder forever. The math behind this is startlingly elegant. When quantum systems decohere, they don't just randomly pick a state, they follow the path of least resistance, a principle called einselection. Applied to the early universe, einselection would have favored configurations where energy was smoothly distributed, setting up the initial low entropy state that fuels time's forward march. This wasn't random luck, it was quantum Darwinism, where only the most stable branches of reality survived the collapse. Support comes from an unlikely place, black holes. When matter falls into a black hole, it scrambles information so thoroughly that physicists once thought it vanished forever, a perfect entropy machine. Yet Hawking showed black holes evaporate, implying time's arrow even in the abyss. Now imagine scaling this down to the universe's first quantum flicker. The same principles that make black holes one-way streets might have imprinted time's direction on the cosmos itself during decoherence, like a seal pressed into cooling wax. Critics argue this just kicks the can. Why did decoherence favor this arrow? Some theorists propose a jaw-dropping answer: it didn't. The multiverse might contain universes with every possible time orientation, and we only perceive ours because conscious observers require entropy's rise to process memory and causality. Try imagining a reality where time flows backward to you. It would just feel like time moving forward because your brain would embed entropy's local rules. This means the arrow isn't universal, just ours, etched into existence when the quantum dice landed a certain way. Experiments are catching up. Quantum simulators can now create tiny, time crystals, systems that oscillate without energy input, blurring the line between past and future. Others are manipulating entangled particles to mimic how decoherence might have locked in thermodynamic asymmetry. If these lab-scale models behave like the Big Bang's math predicts, we might finally understand why time never rewinds, not because it can't, but because the universe's first quantum choice made the other paths unobservable. So the next time you watch milk swirl into coffee, remember, you're not just seeing physics in action. You're witnessing the echo of a 14-billion-year-old quantum decision, where the universe took its first irreversible step from maybe to now. Lab experiments with isolated quantum systems are revealing something extraordinary. The same processes that might have locked the universe into its irreversible timeline are playing out right now on tabletops. Take a vial of supercooled cesium atoms, for example. When physicists isolate these atoms in a vacuum and nudge them into a quantum superposition existing in two states at once, they can watch as interaction with even a single photon causes the system to choose a single state. This collapse isn't random. It follows a distinct thermodynamic path where information leaks irreversibly into the environment, creating a tiny arrow of time where there was none before. In one striking experiment at the University of Maryland, researchers trapped beryllium ions in electromagnetic fields, coaxing them into a superposition of spin-up and spin-down states. By precisely measuring how these states decohered when exposed to controlled noise, they found something eerily familiar. The ions didn't just lose quantum coherence, they did so asymmetrically, mirroring the one-way flow of entropy we see in the macroscopic world. It's as if the act of measurement didn't just observe reality but sculpted it, carving a preferred direction into time itself at the microscopic level. Even more compelling are experiments with superconducting qubits, artificial atoms built to mimic quantum behavior. At Yale's Quantum Institute, scientists observed that when qubits interact with their surroundings, their quantum states don't fade smoothly but jump abruptly from superposition to certainty, like a film skipping frames. These jumps aren't reversible. Once the qubit picks a state, there's no winding back the clock. The kicker, the timing of these jumps follows the same statistical patterns as entropy increase in classical thermodynamics, suggesting a deep link between quantum collapse and the birth of time's arrow. What's fascinating is how these small-scale observations echo cosmological models. Just as a collapsing quantum superposition in the early universe might have favored low-entropy initial conditions, lab systems tend to decohere into states that maximize entropy production. This isn't just analogy, it's mathematical equivalence. The equations governing how a qubit loses coherence to its environment are strikingly similar to those describing how the universe's quantum fog crystallized into a timeline. Critics argue that lab systems are too simple to reflect cosmic-scale physics, but recent breakthroughs are bridging the gap. In 2022, a team at Caltech coupled hundreds of entangled photons in a way that mimicked the inflationary epoch of the universe, observing how decoherence spread like a wave through the system. The result, an emergent arrow of time that grew stronger as the system scaled up, hinting that the irreversibility we experience might just be quantum statistics writ large. These experiments don't just illuminate the past, they challenge our sense of time's inevitability. If a handful of atoms can choose a temporal direction through decoherence, then the universe's arrow might not be fundamental, but the fossil of a quantum decision made when reality was barely a second old. The takeaway is haunting. Time doesn't flow. It's a relic of forgotten possibilities, a shadow cast by choices the cosmos made before the first stars ignited. What if the universe's first quantum superposition didn't collapse randomly, but was observed into existence by something already there? This is the wild premise of Theory 10, that a primordial observer, perhaps a quantum field or even a structure beyond spacetime, acted as the cosmic litmus test, forcing the haze of possibilities to snap into our reality. We usually think of observation as something conscious beings do, but in quantum mechanics, an observer can be anything that extracts information: a particle collision, a measurement device, even the fabric of spacetime itself. At the universe's birth, before stars or atoms existed, some fundamental interaction might have played this role, inadvertently locking in the laws of physics we take for granted. The math behind this is less speculative than it sounds. Quantum decoherence, the process where superposition breaks down, doesn't require a human or even a machine. It just needs interaction. Picture the early universe as a quantum dice mid-roll, with every possible configuration of particles, forces, and dimensions still in play. Then, as the first quantum fields began interacting, perhaps gravity tugging at nascent fluctuations, or the Higgs field rippling through the void, those interactions measured the system, collapsing probabilities into concrete outcomes. It's like a game of dominoes where the first touch doesn't just knock one piece over, but selects an entire universe's worth of falling patterns at once. This idea dovetails eerily with the fine-tuning problem. If the superposition collapse wasn't random but guided by some pre-existing quantum structure, it could explain why our universe's constants seem improbably perfect for life. Perhaps the observer field favored stable, information-preserving states, meaning universes where black holes didn't instantly form or where particles could stably bond were more likely to emerge. Some models even suggest that the act of observation created time's arrow, with the primordial interaction not just selecting a universe but jump-starting causality itself. Critics argue this just pushes the mystery back a step. What observed the observer? But supporters point to loop, quantum gravity, spin networks, or string theory's brains as candidates. These aren't conscious entities, just fundamental structures that could have encoded the universe's rules before spacetime existed. The real mind bender. If true, we might find echoes of this process in the cosmic microwave background's polarization patterns, subtle swirls that could reveal how the first measurement etched order into the void. The implications ripple outward. If observations shaped the cosmos, then the universe didn't just happen, it responded, like a grand quantum experiment where the apparatus and the result were one and the same. It's a humbling thought that the laws we call fundamental might just be the answer to a question the universe asked itself in its first fleeting moment of existence. The idea that consciousness played a role in collapsing the universe's first quantum superposition, cosmic panpsychism, sounds profound, but not everyone's convinced. Critics argue that invoking consciousness as a fundamental force risks veering into metaphysics when straightforward physics might suffice. After all, quantum decoherence shows how interactions between particles, not minds, can resolve superpositions without any mystical observers. Picture a photon colliding with a dust particle in deep space. That collision measures the photon's state, forcing it out of superposition. No conscious being needed, just the cold, impersonal laws of physics at work. This divide splits cosmologists into two camps. One side sees consciousness as an unnecessary addition, like suggesting a ghost pushes planets along their orbits when gravity explains it perfectly. They point to experiments where quantum systems decohere purely through environmental noise, thermal jostling, stray electromagnetic fields, even the hum of quantum vacuum fluctuations. If a jumble of random interactions can collapse a superposition in the lab, why assume the early universe required anything grander? The other camp counters that while decoherence explains how superpositions break down, it doesn't explain why our universe's particular configuration emerged. Out of infinite possible outcomes, we landed in one where the constants allow stars, planets, and life. That seems suspiciously lucky unless something tilted the scales. Panpsychists propose that proto-consciousness, woven into the fabric of reality, acted as a filter favoring stable, coherent universes over chaotic ones. It's not that atoms think, but that the universe's fundamental ingredients might include a bare minimum of experience, enough to nudge quantum possibilities toward complexity. Yet skeptics pounce on the vagueness of this claim. What does proto-consciousness even mean mathematically? If it's just another quantum field, where's the evidence? Detractors argue this is a God of the gaps argument, using consciousness to patch holes in our understanding rather than seeking testable mechanisms. They prefer theories like inflationary cosmology, where random quantum fluctuations during the universe's exponential expansion naturally produce the diversity we see, no observers required. The debate crystallizes around a simple question: is consciousness a feature of the universe or a fluke within it? Panpsychists see it as foundational, like space and time. Critics see it as an emergent property, like hurricanes or flames, spectacular but not fundamental. Both sides agree on one thing: the universe's first quantum moment was strange beyond belief. Whether consciousness played a part might remain unanswered until we crack the hardest problem of all, the nature of awareness itself. For now, the mystery lingers. Maybe the truth lies somewhere in between, a universe where quantum processes built the stage and consciousness later stepped into the spotlight, mistaking itself for the director all along. DNA is often called the blueprint of life, a molecule that encodes every possible trait an organism could develop, from eye color to disease resistance. But what if the universe had its own version of cosmic DNA, written not in chemical bases but in quantum fluctuations? Theory 11 suggests that the universe's first superposition wasn't just a chaotic haze, it was an information-rich probabilistic code, containing every possible structure, law, and configuration reality could take, waiting to be expressed like genes in a cosmic embryo. Think of the early universe as a stem cell, an undifferentiated state brimming with potential. Just as a single fertilized egg contains the instructions to build a heart, a brain, or a fingertip, the primordial quantum field held the seeds of galaxies, black holes, and even the laws of physics themselves. The double helix of DNA encodes possibilities through combinations of 4 bases. The quantum code would have used superpositions of energy states, field values, and spacetime geometries. When decoherence hit, whether through interaction, observation, or some other mechanism, it was like the moment a cell begins to specialize, locking in certain traits while others fade away. Our universe's particular set of physical constants, just one gene switched on from an infinite library. This analogy isn't just poetic. The mathematics of quantum information theory reveals startling parallels. DNA's information is stored in discrete bits base pairs, and so is quantum information measured in qubits, which can exist in superpositions of states. In the early universe, every quantum fluctuation was a kind of cosmic qubit, a probabilistic entry in reality's codebook. Some calculations even suggest that the total quantum information in our observable universe, around 10 to the power of 120 bits, might mirror the combinatorial complexity of a biological blueprint scaled to cosmic proportions. The implications are staggering. If true, the universe's fine-tuning isn't a miracle, it's inevitable. Just as DNA mutates to explore biological possibilities, quantum fluctuations tested every conceivable physics until stable configurations emerged. Universes where gravity was too weak for stars to form. Like genetic dead ends, they faded away. Our universe, with its Goldilocks constants, the equivalent of a thriving organism, its traits selected by the cosmic equivalent of natural selection. But here's the twist: DNA isn't static. Epigenetics shows how environmental factors can turn genes on or off without altering the underlying code. Similarly, traces of the universe's original quantum instructions might still be switchable. Some theorists speculate that dark energy's mysterious behavior could be a kind of cosmic epigenetics, an environmental trigger tweaking the universe's deep code. Others hunt for evidence in quantum entanglement, where particles separated by light years remain mysteriously linked, as if sharing hidden genetic information. The most tantalizing clue might lie in the cosmic microwave background. Biologists reconstruct evolutionary history from genetic drift in populations. Cosmologists could one day reconstruct the universe's quantum mutation history from anomalies in the ancient light. Patterns resembling error-correcting codes like those in digital DNA sequencing have already been spotted in the large-scale structure of galaxies. Are these the fingerprints of reality's first quantum blueprint? Whether metaphor or mechanism, the idea reshapes our origin story. The universe didn't just explode into being, it unfolded like a cosmic organism expressing its deepest code. And just as a single cell holds the potential for a human mind, those first quantum flickers held everything, every star, every atom, every question we've ever asked about where it all began. The universe doesn't just arrange matter randomly, it sculpts it into eerily familiar shapes, like a cosmic artist working from an unseen blueprint. Look at the largest structures we've mapped, galaxies clustered along filaments stretching hundreds of millions of light years, weaving a web so vast it resembles the branching veins of a leaf or the neurons in a human brain. These aren't just coincidences, they might be quantum echoes, ghostly imprints left behind when the universe's first superposition collapsed, freezing fractal geometry into the fabric of spacetime itself. Picture the early cosmos not as a smooth soup, but as a seething quantum foam where fluctuations at the tiniest scales mirrored the grand patterns we see today. At the birth of space and time, quantum fields didn't just flicker randomly, they vibrated in harmonics, like a plucked string creating overtones. When inflation stretched these quantum ripples to cosmic proportions, they didn't vanish. Instead, they became the scaffolding for everything, the slight over densities where galaxies would later bloom, the vast voids between them, even the delicate spirals of individual stars. The universe didn't forget its quantum origins, it painted them across the sky in starlight. This idea isn't pure poetry. The math backs it up. Simulations of the early universe, when fed quantum fluctuations as initial conditions, produce large-scale structures nearly identical to what telescopes observe. The key lies in something called scale invariance, a property where patterns repeat at different sizes, from the quantum to the cosmic. Zoom in on a galaxy cluster's distribution, and you'll see the same branching motifs as the quantum foam's original vibrations, just magnified trillions of times. It's like blowing up a snowflake to planetary scale and finding its symmetry intact. The most striking evidence, the cosmic microwave background's temperature fluctuations. These tiny variations, some warmer, some cooler, aren't scattered chaotically. They follow a precise power law distribution, a fingerprint of quantum processes stretched across space. When scientists compare these patterns to the clustering of galaxies 13 billion years later, the match is uncanny. It's as if the universe whispered its quantum code into the void, and gravity spent eons tracing those words in stars. But here's where it gets stranger. Some physicists speculate that these fractal echoes might not be accidental. If the universe's initial quantum state was entangled, a single, unified network of probabilities, then the large-scale structure we see could be a shadow of that ancient connectivity. Imagine two particles separated at the Big Bang, their fates still entwined by quantum rules. Over cosmic time, their influence would stretch across light years, subtly guiding where galaxies form. This could explain why the cosmos looks less like scattered marbles and more like a carefully woven tapestry, with threads of dark matter tracing paths set in the first quantum instant. Critics argue that gravity alone could sculpt such order, but anomalies persist. Certain galaxy clusters align in ways Newtonian physics can't easily explain, their axes pointing toward unseen vectors like compass needles drawn to a hidden magnet. Others note that the universe's largest structures, colossal walls of galaxies like the Hercules Corona Borealis Great Wall, defy standard models of cosmic evolution. Could these be quantum scars, regions where the superposition collapse left deeper marks? The answer might lie in future sky surveys. Projects like the ESA's Euclid telescope are mapping billions of galaxies with unprecedented precision, hunting for deviations from predicted fractal dimensions. If certain patterns repeat too perfectly, or not perfectly enough, it could signal quantum fingerprints older than atoms, older than light, written when the universe was just a probability waiting to be seen. Until then, we're left with a humbling thought. The stars above aren't just distant suns. They're notes in a song the cosmos has been singing since its first quantum breath. Black holes might seem like cosmic dead ends, places where information vanishes forever. But what if they're actually the universe's original stitching, the quantum threads that sewed spacetime together in the first moments of existence? This is the heart of the ER=EPR conjecture, a radical idea that suggests entangled particles and black holes are two sides of the same cosmic coin. The name sounds cryptic, but it's hiding something profound. Refers to Einstein and Rosen's old idea that black holes could be bridges between distant points in space, while EPR nods to Einstein, Podolsky, and Rosen's famous paradox about quantum entanglement. Mash them together and you get a revelation that the fabric of reality might be woven from quantum connections so deep they predate space and time as we know them. Picture the universe's first quantum superposition not as a chaotic storm, but as an infinite web of entangled particles, each link a tiny wormhole waiting to unfurl. In this view, when the superposition collapsed, those quantum handshakes didn't just vanish, they expanded, stretching into the geometry of spacetime itself. A black hole's event horizon, not a one-way trap, but a cosmic loom where space is continually rewoven from the entanglement of particles at its edge. This would mean the universe didn't emerge into space. It emerged from quantum relationships like a 3D tapestry rising from a flat pattern of threads. The math behind this is as elegant as it is strange. In quantum mechanics, entangled particles share a connection that defies distance measure one, and the other instantly responds even if light years apart. General relativity, on the other hand, describes spacetime as bendable, with black holes warping it into tunnels called Einstein-Rosen bridges. ER=EPR merges these ideas. What if entanglement is the wormhole just viewed through quantum eyes? Those spooky action at a distance links might literally be tiny bridges in spacetime, too small to see but fundamental to reality's structure. If this conjecture holds, it rewrites cosmic history. The early universe wouldn't have needed inflation to smooth itself out. Those quantum threads would have already tied everything together, ensuring coherence without faster-than-light expansion. Even the Big Bang's low entropy makes eerie sense. A highly entangled state naturally resists disorder, like a perfectly organized network refusing to fray. And when the superposition collapsed, it didn't sever those links, it amplified them, knitting the quantum web into the spacetime we now call home. But how would we test something so abstract? Clues might hide in the firewall's paradox, a debate about whether black holes destroy information at their edges. If ER=EPR is correct, there'd be no firewall. just a seamless transformation where particles crossing the horizon remain entangled with their partners outside. Experiments with quantum computers are already simulating tiny, holographic black holes, watching how entanglement mimics spacetime geometry. And gravitational wave detectors could one day spot anomalies in merging black holes. Subtle tremors that reveal their interiors are threaded with wormholes, not singularities. The wildest implication: if spacetime is built from entanglement, then the universe's first superposition wasn't just a moment, it was the first stitch in a cosmic quilt that's still growing. Every new black hole, every quantum link adds another thread to the pattern. We're not just living in space, we're living inside a quantum handshake that's 14 billion years old. Scientists are now racing to test this mind-bending connection between entanglement and spacetime by recreating microscopic wormholes in the lab, not with gravitational forces but with quantum trickery. At the California Institute of Technology, researchers have built an analog system using superconducting qubits, artificial atoms that can be coaxed into entangled states. By carefully manipulating these qubits, they've created a quantum circuit that mathematically mirrors the behavior of a traversable wormhole, complete with signals appearing to jump between points without crossing the intervening space. The experiment works like a cosmic sleight of hand, when two qubits are maximally entangled, sharing a quantum link so strong that measuring one instantly defines the other. Their connection can be mapped onto the equations describing an Einstein-Rosen bridge. Input a quantum state into one qubit, and it emerges scrambled from its partner, just as information might appear distorted after traversing a wormhole's chaotic interior. Last year, the team observed this teleportation effect while measuring negative energy signatures, a key ingredient for keeping theoretical wormholes stable. It's not a genuine spacetime tunnel, but a shadow play revealing how entanglement might encode geometry. Meanwhile, at Harvard, another approach uses ultra-cold atoms in optical lattices to simulate wormhole dynamics. Here's where it gets surreal. By tuning lasers to mimic the gravitational field near a black hole's event horizon, physicists can watch how entangled particle pairs behave when one falls in. According to ER equals EPR, the partner outside should exhibit subtle changes in quantum noise patterns that would mirror information squeezing through a microscopic wormhole. Early results show exactly these telltale fluctuations, hinting that spacetime's fabric might really be woven from quantum connections. But the most ambitious test is underway at Fermilab, where the holometer experiment is hunting for direct evidence that spacetime has a quantum structure. By firing lasers down perpendicular 40-meter tunnels and measuring interference patterns at unimaginably tiny scales, scientists hope to catch spacetime pixelation, the jitter that would exist if reality is built from finite entangled bits. Finding this noise would support the idea that the universe's smooth spacetime emerged from a deeper quantum network, like a digital screen's crisp image arising from discrete pixels. Critics argue these analog systems are just fancy metaphors, that until we observe actual spacetime warping, the conjecture remains speculative. Yet proponents counter that quantum simulations have a track record of revealing profound truths, from superconductivity to quark-gluon plasma. If entanglement truly underlies geometry, then probing one gives us indirect but meaningful insight into the other. The ultimate goal: a tabletop experiment where manipulating entanglement visibly alters spacetime's properties, perhaps by creating a measurable delay in light's travel time between entangled photons. What makes these tests revolutionary isn't just their boldness, but their implication that the universe's first quantum state might still be echoing through every entangled particle, every black hole, every inch of spacetime we call home. The wormholes we're trying to create may not lead to other stars, but they might help us glimpse the quantum loom that wove reality itself. What if the universe is the ultimate free lunch, a cosmic magic trick where the sum total of everything from stars to black holes adds up to precisely zero? This is the zero-energy universe hypothesis, a mind-bending idea that the cosmos emerged from nothingness by perfectly balancing positive and negative energies in its first quantum superposition. Picture the early universe not as a violent explosion of matter, but as a meticulous accountant's ledger where every particle's energy was offset by an equal and opposite gravitational debt. Stars, galaxies, even your own body, just entries on a balance sheet that ultimately zeroes out. The math behind this is deceptively simple. Einstein's general relativity reveals that gravity isn't just a force, it's negative energy woven into spacetime's curvature. When you drop a ball, it gains kinetic energy, but Earth's gravitational field loses an equal amount. Scale this up to the entire cosmos, and something extraordinary happens. The positive energy locked in matter and radiation is exactly cancelled by the negative energy of gravitational attraction. Nobel laureate Richard Feynman once illustrated this with a thought experiment. Imagine building a universe by gathering matter from infinitely far apart. The gravitational work required to assemble it would subtract exactly the energy the matter contains, leaving the books balanced at zero. This isn't just numerology. Quantum field theory shows that particles constantly blink in and out of existence from the vacuum, borrowing energy briefly before vanishing again. Apply this to the Big Bang, and you get a compelling scenario. The universe's initial quantum superposition wasn't a random fluctuation, but a perfectly self-canceling wave of possibilities. One branch might have contained a surplus of matter, another dominated by negative curvature, but the version that stabilized our universe landed on the razor's edge of equilibrium. It's as if reality is a grand cosmic equation that solved for zero, with galaxies and black holes as the working out of the problem. Critics argue this ignores dark energy's accelerating expansion, but here's the twist: dark energy might be the universe's way of maintaining balance. As matter dilutes with expansion, dark energy's repulsive effect grows proportionally, keeping the total energy hovering near zero across billions of years. Some models even suggest dark energy is the quantum interest on the universe's original loan from nothingness, a small but persistent adjustment keeping the books balanced. The implications rewrite our origin story. If the universe truly sums to zero, then its birth required no external energy input, just a quantum fluctuation so perfectly symmetrical it birthed everything from nothing. This could explain why something exists rather than nothing. Universes that didn't balance their books likely collapsed instantly, while ours endured by threading the ultimate needle. Next time you feel insignificant, remember, you're not just stardust, you're part of the universe's most audacious accounting trick, a masterpiece of self-canceling quantum possibilities that somehow added up to everything. The quantum vacuum isn't empty, it's a seething ocean of potential where particles flicker into existence and vanish again so quickly they barely leave a trace. These virtual particles aren't just a curious side effect of quantum mechanics, they might be miniature echoes of the universe's first moment, tiny rehearsals of the cosmic drama that birthed reality itself. Imagine the early cosmos not as a static singularity, but as a boiling quantum foam where space and time themselves were unstable, birthing and annihilating entire universes in fleeting instants. Our universe could be the rare fluctuation that didn't immediately snap back into nothingness, a cosmic jackpot where the quantum vacuum's chaos accidentally struck gold. At the heart of this idea lies a profound symmetry. Virtual particles arise from Heisenberg's uncertainty principle, which allows energy to be borrowed from the vacuum so long as it's repaid quickly. Particle-antiparticle pairs blink into existence, dance for unimaginably short periods, then annihilate, balancing the books. Now scale this up to the Big Bang. What if the entire universe was once a quantum fluctuation on an unimaginable scale? A temporary imbalance in the vacuum's accounting that, through some twist of physics, never had to pay its debt back. Inflationary theory hints at this. a runaway expansion fueled by a peculiar state of the quantum vacuum called a false vacuum, where repulsive gravity stretched a subatomic speck into a cosmos in less than a trillionth of a second. The evidence hides in plain sight. When physicists measure the Casimir effect, the faint force between metal plates caused by virtual particles pushing from the outside, they're glimpsing the same quantum restlessness that might have powered cosmic genesis. Even black holes, those voracious devourers of matter, leak energy via Hawking radiation, a process where virtual particles near the event horizon steal enough energy to become real, slowly evaporating the whole. It's as if the universe never forgot its origins, replaying its first quantum trick on every scale, from the infinitesimal to the galactic. But here's the twist: if virtual particles can birth universes, then our cosmos might not be unique. Some theories suggest that bubble universes constantly nucleate in the quantum foam, each with its own physics, sprouting from vacuum fluctuations just as ours did. Most would collapse instantly, but a rare few, through sheer statistical luck, might stabilize into full-fledged realities. This transforms the multiverse from a philosophical guess into a thermodynamic inevitability. Given infinite time and quantum chance, even nothingness must eventually cough up something. The implications are dizzying. The same quantum jitter that makes empty space sparkle with virtual particles might also have written the first draft of reality, a draft where every law of physics, every constant, was just one roll of the dice in a game the vacuum has been playing since before time began. Next time you stare at the night sky, remember, the stars aren't just burning gas. They're the afterglow of the universe's first quantum gamble, a bet against nothingness that against all odds paid off. The Boltzmann brain paradox presents one of the most unsettling possibilities in all of physics, that the universe's first quantum superposition might have randomly assembled self-aware observers long before galaxies ever formed. Imagine a lone, disembodied brain floating in the void, complete with false memories of a life that never existed, conjured into being by sheer quantum chance. This isn't just science fiction, it's a legitimate prediction of statistical mechanics. If the early universe was a quantum dice roll across infinite configurations, the most likely conscious observers wouldn't be beings like us, embedded in rich cosmic structures over billions of years. They'd be momentary aberrations, Boltzmann brains popping into existence just long enough to ask, "Where am I?" Before dissolving back into chaos. The math behind this nightmare scenario comes from Ludwig Boltzmann, the 19th century physicist who revolutionized our understanding of entropy. He realized that given enough time, even the most improbable states will occasionally arise from random fluctuations. Apply this to quantum cosmology, and the implications are staggering. In an infinite multiverse, or even just an eternally fluctuating vacuum, the probability of a fully formed brain spontaneously assembling from quantum noise, complete with sensory input convincing it of a fake reality, far exceeds the odds of an orderly universe like ours evolving naturally. Statistically, Boltzmann brains should outnumber real observers by an unimaginable margin. So why don't we find ourselves adrift in the void, hallucinating stars that aren't there? One terrifying answer is we might be. There's no foolproof way to prove you're not a Boltzmann brain right now, living out an elaborate illusion, but physicists have devised clever escape routes. The most compelling comes from actually embracing the paradox. If Boltzmann brains dominate the cosmos, then their false observations would drown out legitimate data, making the universe appear far more disordered than we observe. The fact that we measure such stunningly low entropy, pristine cosmic microwave background, predictable planetary orbits, suggests we're part of a statistically unlikely but coherent timeline. Our very ability to trust scientific measurements implies we're probably not quantum phantoms. Another clue hides in quantum decoherence. For a Boltzmann brain to arise spontaneously, it would need to maintain coherence long enough to form complex neural patterns, an absurdly tall order in a high-entropy vacuum. Calculations show that even if such a brain flickered into being, environmental noise would destroy its delicate quantum states before coherent thought could emerge. Real conscious observers, by contrast, are stabilized by their immersion in an ultra-low-entropy universe where atoms reliably bond into stable structures over billions of years. The persistence of memory, the consistency of physical laws, these aren't just happy accidents. They're signatures of a reality that didn't cheat its way into existence through a quantum fluke. Yet the paradox lingers like a ghost in the equations. Some theorists speculate that the universe's first superposition didn't just collapse into our reality. It actively suppressed Boltzmann scenarios by selecting for configurations where coherent, long-lived observers could emerge. This anthropic selection pressure might explain why we find ourselves in a cosmos with galaxies rather than chaos. Others propose that the holographic principle places fundamental limits on how much information can spontaneously appear in a vacuum, making Boltzmann brains mathematically impossible. The debate rages, but one thing is certain: the fact that we're here debating it at all is the strongest argument that we're probably real. After all, a Boltzmann brain's solipsistic nightmare would be far simpler. Just enough complexity to ask the question, not to build telescopes, run experiments, and collectively unravel the universe's deepest mysteries. So next time you question reality, take comfort in the messiness of existence, the laundry piling up, the traffic jam, even the inexplicable popularity of pineapple pizza. A Boltzmann brain wouldn't bother with such gloriously mundane details. It would be too busy hallucinating equations in the void, desperately trying to convince itself it was real. The universe may have begun as a quantum gamble, but the odds that we're the house, not the dice, just keep getting better. The Boltzmann brain paradox isn't just a thought experiment. It's a fracture in our understanding of reality that forces physicists to ask uncomfortable questions. If the universe truly began as a quantum superposition of all possible states, why didn't it collapse into chaos? Why are we here, embedded in a cosmos with galaxies, planets, and predictable laws, rather than drifting in a void as fleeting aberrations? The answer might lie in a principle so subtle it's often overlooked: typicality. Imagine you're dealt a hand of cards. Getting a random mix of hearts, spades, and diamonds is unremarkable. But being dealt a perfect royal flush feels suspiciously lucky. The typicality argument suggests our universe isn't that royal flush. It's the unremarkable hand, the statistically expected outcome of a quantum collapse that favored stability over chaos. In the infinite multiverse of possibilities, most observers would find themselves in universes where the laws of physics permit complex, enduring structures, simply because disordered realities rarely support consciousness long enough to ask questions. Boltzmann brains, by contrast, are vanishingly rare, not because they're impossible, but because they're like cards shuffled into a perfect sequence by chance. Possible but profoundly unlikely, critics pounce on this reasoning, calling it a cop-out. If typicality explains our orderly universe, why does it feel so finely tuned? The constants of nature seem suspiciously perfect for life, like a lock engineered for its key. One counterargument comes from cosmology's measure problem, the challenge of defining probabilities in an infinite multiverse. Without a way to weight outcomes, all possibilities, no matter how absurd, might have equal claim to reality. Typicality advocates respond by invoking quantum decoherence. The process that collapsed the universe's initial superposition didn't sample possibilities randomly, but filtered them through interactions that naturally suppressed high-entropy states. Think of it like a cosmic sieve, where only configurations with stable information processing, like galaxies forming over billions of years, made it through the mesh. Support for this view comes from an unexpected place: black hole physics. The holographic principle suggests the maximum entropy of any region isn't determined by its volume, but by its surface area, a limit that would have constrained the early universe's quantum chaos. Calculations show that in such a bounded system, stable, low-entropy states like ours aren't just probable, they're inevitable, because higher entropy configurations would have exceeded the universe's information budget. It's like trying to stuff an infinite library into a finite room. The only viable solutions are the ones where books are neatly shelved, not exploding in chaos. Yet the debate is far from settled. Some theorists propose that Boltzmann brains are the norm, and our perceived reality is an illusion. They argue that even if these disembodied observers are rare, their sheer numbers in an eternal multiverse would dwarf real beings like us. The rebuttal: consciousness might require more than just a lucky quantum fluctuation. A brain without sensory input, memory, or a consistent environment would have no way to ground its perceptions in anything resembling reality. Hallucinating a whole cosmos is orders of magnitude harder than simply existing in one. The most compelling evidence against the paradox might be the universe itself. The cosmic microwave background's exquisite uniformity, the precise balance of forces allowing atoms to exist, these aren't the hallmarks of a random fluctuation. They're signatures of a quantum collapse that privileged structure over noise. If Boltzmann scenarios dominated, we'd expect to see far more disorder in the oldest light we can observe. Instead, we find a cosmos that's suspiciously well-behaved, like a student who didn't just pass the test but aced it with celestial precision. In the end, the paradox may reveal less about the universe's origins and more about the limits of human intuition. Our brains evolved to spot patterns in a middle-sized world of trees and predators, not to navigate quantum probabilities across infinity. The fact that we're here pondering these questions at all suggests one thing: the universe's first quantum roll of the dice didn't land on chaos. It landed on us, and that's anything but random. Black holes aren't just cosmic dead ends, they might be cosmic cradles. The black hole origin theory flips everything we thought we knew about singularities, proposing that our entire universe isn't just like a black hole's interior. It is one born from the quantum chaos of a singularity in some higher dimensional reality. Picture this: in the moment before our Big Bang, a massive black hole in a parent universe collapsed inward, reaching densities so extreme that the very fabric of spacetime shattered like glass under pressure. Inside that singularity, where general relativity breaks down and quantum gravity takes over, the laws of physics as we know them didn't just pause, they rebooted, creating the perfect conditions for superposition to unfurl into an entirely new cosmos. This isn't pure speculation. The math reveals eerie parallels between black hole physics and cosmic genesis. When matter crosses a black hole's event horizon, time and space swap roles. What was once a direction in time becomes a direction in space, and vice versa. From the perspective of someone inside the black hole, the singularity isn't a point in their future. It's a moment in their past. Sound familiar? It's the exact reverse of our Big Bang, where all matter and energy erupt from a single point in our past. Some theorists argue this isn't coincidence but evidence. Our universe might literally be the interior of a black hole in another reality. Its singularity, our Big Bang; its event horizon, our cosmic horizon. The quantum twist comes when you consider what happens at the scale of a singularity. Under normal physics, singularities are where calculations explode to infinity. But if quantum gravity smooths them out, as loop quantum cosmology suggests, that infinite density could resolve into a frothing quantum foam. In this foam, every possible configuration of spacetime and matter exists in superposition, an infinite set of potential universes waiting to be born. When this quantum storm collapsed, it didn't just produce a universe, it produced ours with its specific constants and dimensions, while other branches might have spawned realities with entirely different laws. Support for this idea comes from unexpected corners of astrophysics. The observable universe's total mass energy matches predictions for what you'd expect inside a stellar mass black hole's interior. Even the cosmic microwave background's uniformity, a puzzle for classic Big Bang theory, makes sense if our universe inherited its structure from the quantum fluctuations of its parent black hole's event horizon. Like a hologram storing 3D information on a 2D surface, those fluctuations could have imprinted onto our newborn cosmos, seeding the galaxies and voids we see today. But the wildest implication isn't about origins, it's about destiny. If our universe is inside a black hole, then every black hole within our cosmos might contain its own nested universe, a fractal chain of realities birthing realities. This transforms black holes from devourers of light into cosmic matryoshka dolls, each hiding a new space-time in its depths. Some models even suggest that the dark matter puzzling astronomers could be the gravitational echo of these parent universes, their mass leaking through the quantum stitches that bind realities together. Of course, skeptics demand proof. How would we ever see beyond our cosmic horizon to spot the parent universe? The answer might lie in gravity waves. If the black hole origin theory is correct, mergers between supermassive black holes in our universe could create ripples in space-time carrying faint imprints of their own internal structure, subtle fingerprints of the quantum bridge between realities. Others propose hunting for anomalies in the cosmic microwave background's polarization patterns, which could encode traces of the pre-Big Bang geometry. Until then, the theory remains a breathtaking possibility that every black hole is a universe in waiting, and our entire cosmic story, from the first quantum flicker to the last dying star, is just one page in an infinite book written in the language of singularities. White holes, black holes, theoretical twins aren't just cosmic afterthoughts. They might be the universe's ultimate rebirth mechanism, spewing out matter and energy too fast for anything to re-enter. If black holes are the cosmic drains, white holes are the fire hoses, violently ejecting everything they contain. Now imagine this: what if our Big Bang wasn't just a singularity exploding outward, but a white hole's final act, a quantum ejection so powerful it birthed an entire new universe? The math behind white holes emerges naturally from Einstein's equations, just like black holes but with time reversed. Where a black hole's event horizon only lets matter in, a white hole's horizon only lets matter out. For decades, physicists dismissed them as mathematical curiosities, since they violate the second law of thermodynamics by seemingly decreasing entropy. But in the context of quantum gravity, white holes take on a startling new role as the birth canals of daughter universes. Here's how it could work. When a black hole in a parent universe forms and evaporates via Hawking radiation, its final moments might not be oblivion, but a quantum bounce. The crushing singularity at its core could rebound as a white hole in a new spacetime, ejecting its contents as the seeds of a fresh cosmos. This isn't just poetry. Loop quantum gravity calculations show that under extreme quantum pressure, collapsing matter can reach a minimum size before rebounding, like a spring compressed to its limit. Apply this to a black hole's demise, and you get a scenario where the dying singularity doesn't vanish but flips inside out, birthing a white hole in another dimension. The mind-blowing part: the new universe's physical laws might inherit quantum imprints from its parent, like cosmic DNA passed through the singularity. Observational clues could be hiding in plain sight. If our universe erupted from a white hole, its earliest moments would carry distinct signatures and absence of true randomness in the cosmic microwave background, or anomalous hotspots where the ejection was most violent. Some theorists speculate that certain high-energy gamma-ray bursts, explosions too powerful to fit current models, could be white holes briefly flickering into existence before collapsing. Others hunt for gravitational wave echoes, subtle ripples that might betray a pre-Big Bang spacetime structure. The most tantalizing possibility: white holes might not be one-time events. If black holes in our cosmos spawn their own daughter universes, we could be part of an infinite fractal chain, each reality nested inside another like layers of an onion. The cosmic microwave background's mysterious cold spot, a vast, unexplained region of cooler radiation, might even be the umbilical scar where our universe connected to its parent. Of course, skeptics argue white holes are still speculative, no definitive observations exist. But with next-generation telescopes probing the early universe's faintest whispers, we might soon catch a glimpse of our cosmic parent's final breath, frozen in the patterns of the sky. Until then, white holes stand as a breathtaking reminder. The universe might not just expand, collapse, and fade. It could be reborn over and over in a cycle of quantum ejections, stitching new realities from the ashes of the old. From holographic births inside black holes to cosmic reboots via white holes, from quantum DNA encoding reality's blueprint to Boltzmann brains hallucinating existence into being, we've journeyed through a labyrinth of possibilities where the universe's first quantum moment isn't just a scientific mystery, but a canvas for the wildest frontiers of human imagination. Each theory we've explored isn't merely a guess, it's a radically different lens on reality's origins, a unique way of asking, what flickered in the darkness before time began? Some frameworks, like loop quantum gravity's bouncing cosmos, treat the Big Bang as a cosmic rebound, while others, like Penrose's conformal cyclic cosmology, see it as a recurring hinge between infinite eons. The holographic principle shrinks creation to a 2D code etched on spacetime's edge, while black hole genesis theories inflate our universe into the interior of a singularity from another reality. And then there's the simulation hypothesis, where the quantum haze was just a loading screen, and dark energy the universe's way of balancing its existential spreadsheet. What's astonishing isn't just the diversity of ideas, it's how each one reconfigures our place in the cosmos. Are we accidental travelers in a multiverse of infinite dice rolls? Or inevitable witnesses in a reality fine-tuned for consciousness? Maybe we're quantum echoes in a hologram or glitches in an alien supercomputer. The beauty is that these aren't mutually exclusive. Physics at the edge of creation is a realm where multiple truths can coexist, each valid within its own mathematical tapestry, each revealing another thread in the grand weave of existence. Now, over to you. Which of these cosmic origin stories resonates most? Do you see the universe as a quantum fluctuation that beat impossible odds, or a hologram projecting from some deeper code? Perhaps you're drawn to the eerie elegance of black holes birthing new realities, or the haunting possibility that consciousness itself shaped the laws of physics. Drop your thoughts below. We're all stardust trying to read its own recipe, and every perspective adds light to the mystery. If your curiosity is buzzing, don't let it stop here. The universe is full of unanswered whispers, from dark matter's hidden grip to the enigma of time's arrow. Hit subscribe and let's keep unraveling them together. After all, the cosmos didn't reveal its first quantum secret in a day. Why should we? The next breakthrough might be just one video.